case of work done by forces that are called conservative forces. And when we have conservative forces, we associate potential energy with those forces. And potential energy in general is energy that's associated with some configuration of a system of objects. And those objects exert forces on one another, and those forces, or what we're going to call the energy that is in the system, is energy that's stored due to the position of the objects with respect to one another. So the first type of potential energy that we're going to talk about is gravitational potential energy. And so we're going to look at the work that's done by gravity on two identical blocks. So I have block A here and block B here that's at the top of an incline. And we could imagine that we release both of these blocks from rest. And of course, block A would just travel straight down in the vertical direction. And block B would travel down the incline. And we're going to assume that we don't care about friction and that this surface is very smooth. And we are going to ask ourselves, what is the work specifically done by gravity in both of these cases? So if we look at block A, the work done by gravity is just the force of gravity times the displacement times cosine of the angle. And so if our height here is some height h, and the object is traveling down, then the displacement is going to be a value h, and our force of gravity is in the same direction as the displacement, so the angle there is going to be 0. So the force of gravity is just mass times gravity, displacement is the height h, and then we have cosine of the angle of 0, which is just 1. And so we get the work done by gravity here is just mass times gravity times my initial vertical position here, which is just the height, where our final vertical position we could say this is like y equal to 0, and this is y equal to h. We can go through the same process for block B, and we can determine what the work done by gravity is as it travels along the incline. So my displacement in this case is this distance L down the incline. My force of gravity is still the weight, but the angle between the force of gravity, which is vertically down, and the displacement, which is down the incline, is this angle here, which is 90 degrees minus theta, where the angle of our incline with respect to the horizontal is our angle theta. So if I plug in the force of gravity is mass times gravity, and I plug in the displacement is L, and then I have cosine of 90 degrees minus theta. Well, it turns out that using one of the trig identities, cosine of 90 degrees minus theta is the same thing as sine of theta. So as I look at this incline and I look at the angle here, it's a right triangle. And so sine of the angle is just the opposite side, which is the height, divided by the hypotenuse, which is the length. So sine of theta is h over L. And if I plug that in here, the L's cancel out, and the work done by gravity on block B is also mgh. So it doesn't seem to matter which path the block travels, whether it's straight down or down the incline. The work done by gravity is exactly the same. And that's because the force of gravity is only helping it move in the vertical direction. And so if we think about the fact that, there is a component of the force of gravity that's acting down the incline and a piece that's perpendicular, only that component that is acting down the incline is actually helping it move down the incline. But in general, it doesn't even matter because the work done by gravity is path independent. In both of these cases, it is just dependent on where we started, which was our initial position. Our initial vertical position is this height h. And then where we end up, where the block ends up, which is at the bottom, which is our vertical final position y. So the work done by gravity is independent of the path. So in general, we can write the work done by gravity as mgh. That's one way it's written. But in our case, our h is just the difference between where we started vertically. So this is our y-axis. So y initial minus y final. And we can always write the work done by gravity in terms of just our vertical starting position and our vertical ending position. And we don't have to worry about if it's traveling down an incline, if it's traveling on some curved surface. The work done by gravity is always just going to depend on where you start and where you end up. So whenever the work done by gravity is path independent, we do say that it's a conservative force, and anytime we have a conservative force, we associate a potential energy with it. So this is energy due to position. It's called gravitational potential energy because the force that we're looking at the work for is the work of gravity. And so if we look at the expression here for the work done by gravity, it depends on mass, gravity, and vertical position. So we define gravitational potential energy as mass times gravity times the vertical position y. Now we have to have some reference, like where is our coordinate system? In other words, we have to have some origin of our coordinate system, and we can actually choose that wherever we want. Typically we choose the lowest position to be the y equal to 0. So in this case, my final position here would be my y equal to 0, and my initial position here would have been y initial equals h. According to the work energy theorem, we know that the net amount of work done by any forces on our system is just equal to the change in kinetic energy. So in our case, we have work done by gravity, which simply depends on the force of gravity and our displacement along the vertical. And that would result in a change in kinetic energy final minus kinetic energy initial. If the blocks are released from rest, then we can think about this as the potential energy that we have to start with, mgh, because our initial height is h and our final position is 0. Our initial potential energy is just equal to our final kinetic energy. And this is assuming that there's no friction or any other forces that would be doing work on our system. So what does this tell us? This tells us that because they both blocks have the same potential energy to start with and the same work done by gravity, essentially, they will have exactly the same speed when they get to the bottom. They'll be traveling in a little different direction because the block B will be traveling down the incline when it gets to the bottom, but they will have the same speed. And this is an example where stored energy from the force of gravity, which is potential energy, and here I forgot to write this as a U, is converted into kinetic energy. And this is just K. So as I mentioned, whenever work done by a force is path independent, meaning that when you figure out the work done by the force, it only depends on where you start, your initial position, and your final position. Any force that has work done in this particular case, where it is path independent, is called a conservative force. And there are very few conservative forces in nature. The gravitational force is one of those forces. Anytime we do have a conservative force, we always associate a potential energy with that particular force, and it is energy due to position. So like for gravity, we have potential energy because it is raised above some ground level, some reference level, and because of that it has potential energy. We're going to find that we also have potential energy due to springs, and there's some others that we would see when we start to talk about electricity. So in general, we can write the work done by gravity as just the potential energy initial, mgy initial, minus the potential energy final, mgy final. So this is just potential energy initial minus potential energy final. And anytime we have the difference between final and initial, we always write that as a change. Now in this case, it's initial minus final. So the work done by gravity is just the negative of the change in potential energy. And we're always going to care about changes in potential energy, meaning that we can choose our reference wherever we want, and then everything is measured with respect to that reference, and we can think about how the object's vertical position changes relative to that reference. One thing that we do notice is that if we have a closed path, meaning that we go back to where we started, that the work done is going to be 0. So the work done by gravity when the initial position is exactly equal to the final position is just 0. And we say that the work done by conservative forces on a particle that moves in a closed path is always going to be 0. And it's always going to be 0 because the work done only depends on where you start and where you end up at some position. And if you end up back where you started, then the work is going to be 0 always for conservative forces. So we're going to look at an example here in a minute, but one thing to keep in mind is that when we're solving problems, we have to choose a reference for our configuration for the potential energy. And typically we choose that reference value to be the lowest point in the problem. But it is really completely arbitrary because we are interested in the difference in potential energy. But if you have an example and you want to say, all right, well, what's my potential energy? You have to say with respect to what. So I'm going to give a visual example. Imagine that there was a table and then I had a tennis ball. And if I was holding the tennis ball above the table, I would say, well, the tennis ball has some potential energy relative to the top of the table. So if I took the top of the table to be my 0, then I would measure my potential energy relative to that, where I'm holding the tennis ball. If I move the tennis ball away from the table and I just hold it above the ground, then I might say that, well, I'm going to measure my potential energy relative to the ground, and then I would have a different amount of potential energy. But I don't really care so much about the actual amount of potential energy. I care about how it changes. So if I'm looking at the difference between where the ball starts and where it ends up when it moves some vertical distance, that difference is going to be the same whether I measure it from the tabletop or I measure it from the ground. So here's just a little bit of an explanation of why I have this stored energy. So imagine that I have a bucket here and I have a string that's attached that goes over a pulley. And I can imagine that I apply a force on this side and I pull the bucket up at a constant speed. So I would need to apply a force that would be equal to the weight of the bucket in order to have it move up at a constant speed. And so the work that would be done by this force would just be the force times the distance that you pull it, or the displacement. Now there's times cosine of the angle, but the force is in the same direction as the displacement. So the work would just be the force times the distance. In this case, the distance that I pulled down here is the same as the distance that the bucket rises up here to some value h. So the work that would have to be done to raise this bucket up to this height here, h, would be mgh. So essentially what's happening is that energy is being put into the system by this external force. And I could write this as the energy in is equal to the work that's done by this applied force here. So if I choose the reference position to be the lowest position of the bucket down here, then the initial potential energy of the bucket is 0. And then once it is raised up to some height, there's some final potential energy. So the fact that we put energy into the system resulted in this bucket having potential energy after it's raised up. So the result is that there is stored energy in this system, and that stored energy is just the final potential energy minus the initial potential energy. And since my final position is h and my initial position is 0, the amount of stored energy is just mgh. Now, if the force is removed and the bucket is released from this height h, then there's energy stored in the form of potential energy at the top, and that energy can be then converted into kinetic energy. So work is done by gravity now on this bucket, and the work done by gravity is just the force of gravity times the displacement times cosine of the angle. Here the force of gravity is acting down, the displacement is down, so the work done by gravity is just the force times the distance, which is h, or d. But this is exactly the same thing as the change in potential energy, or minus the change in potential energy. So the work done by gravity is just the potential energy initial, mgh, minus the potential energy final, which is 0. So either way we calculate the work done by gravity, whether it be looking at the initial potential energy in the final or looking at the force, we get the same result. So once it's released, the energy that was stored in the system in the form of potential energy can be converted into kinetic energy, which is energy due to motion, based on the work energy theorem. So in this case, the work done by gravity, and we have that work or that energy stored in the form of potential energy because we put energy into the system to lift the bucket, and then it has energy associated with it, and that can be converted into the kinetic energy. All right, so let's look at a simple example. So I have a ball that has a mass of 0.25 kilograms, and it's dropped from the second floor of a science building that it has a height of 15 meters. Obviously, this is not drawn to scale. What is the potential energy of the ball when it is located on the second floor and when it is located on the ground? So the first thing we have to do is choose our reference point for our potential energy. And so we might as well choose the bottom or the lowest point to be our 0 value for y, which means that we are starting off above the ground, which is 0, 15 meters. So we know gravitational potential energy is just mass times gravity times our vertical position. So our initial gravitational potential energy would be 0.25 kilograms times gravity, 9.8 meters per second squared, times the height of 15 meters, which would be 36.75. The final gravitational potential energy would just be 0 because I'm on the ground, or just before I hit the ground. So the next question says, what is the work done by gravity during this process? So we know that the work done by gravity is just minus the change in gravitational potential energy. So this is just minus the final potential energy minus the initial potential energy. Final potential energy is 0. Initial potential energy is 36.5. So the work done by gravity is 36.75 joules. You could also have said it's the initial potential energy minus the final, either way. Finally, it says, can we say anything about the change in kinetic energy of the ball as compared to the work done? And according to the work energy theorem, the net amount of work done by any forces has to equal the change in kinetic energy. The only force that's doing work is gravity. So the work done here by gravity is 36.75, and that's going to have to equal the change in kinetic energy. So if we know the work, we always know the change in kinetic energy.